Please do confirm once that I'm visible, I'm audible. You can see me, you can hear me as well, and you can see the screen. Is it audible? Is it visible? Please do confirm once. Okay, okay, okay. I hope there is no issue with the voice now. And if there is any issue, please do tell me. Okay. So let us go through some theoretical fast part first. Then, likewise, we have done in the previous session. We'll be solving some of these questions. Okay. Some of the objective type of questions I have prepared for you all, okay, to solve. We'll go through them. But let us first look through some theoretical aspects of the course. Okay. Everyone, please do confirm once that there is no issue with the audio. In the earlier meeting, we faced some of the issue. That is why I am asking. If anybody is having any issue, then please do tell me. Otherwise, we can continue. All clear? Okay. Okay. Let us begin. Okay. See here. We'll try to see. First of all, what are discrete probability distributions? Okay. In the previous lecture, we have solved some of the questions based on the binomial distribution, as well as in this session, we'll solve some of the questions based on the Poisson distribution. These are all discrete probability distribution. Discrete probability distribution describe the probabilities associated with a random variable that can take only countable values. Likewise, 0, 1, 2, 3, unlike continuous distributions. Okay. Discrete distributions are used when the outcomes represents count of events, component, failure. A failure will be either failure or not failure. Okay, 0 or 1. That is the meaning here. Okay. Deferred or successful operations. So reliability engineering will be dealing with some of the questions which are how many sensors they have failed. Okay, that is one of the question, or how many number of failures we are foreseeing. So likewise, the questions will be there. Okay, how many sensors have failed? How many defective products exist in a batch? Okay, so likewise, the questions will be there. Okay, that is for you to just understand. Okay, how long the first failure will occur. Okay, regarding this, we just have solved one of the question based on in the previous week also. Okay, how many failures are expected during the system operation, and how many inspections are needed before observing a specified number of failures? That is what we just want to ask and answer with. Okay. Each of the questions correspond to a different probability distribution because experimental conditions they generally differ. Okay. Selecting the correct distribution is more important than solving the numerical calculation because in real-time problems, okay, the such data and simplification won't be provided to you. You just have to think. that which distribution I have to apply and which is the distribution which I should go with. Okay. So this is one of the aspect. Okay. In general, these are the notations. Okay. You can change the notations also based on your convenience. Okay. Small n generally denotes number of trials. Small x is the observed number of successes or the events. P is the probability of success. Q is the probability of failure. Or uh, Q is 1 minus P. Okay. Lambda is average number of events per interval. Capital N is the population size. Capital M is the number of successes in the population. K is the required number of successes. That is the negative binomial. Okay. How to choose a particular correct distribution? First of all, start fixed number of trials if they exist. Okay. If the probability is so, then whether the events are independent, if they are independent, the distribution will follow a binomial pattern. Okay. The event will follow a binomial distribution. Okay. No, then this comes under the case of hypergeometric distribution. Okay. So here the line of the flow chart regarding the yes ands. Okay. If it is no, then you have to ask the question counting events in the time. Okay. If you are counting events in the time, then you go with Poisson distribution. If you are waiting for first success, you go with geometric distribution. And if you are waiting for KS success, you go for negative binomial distribution. Okay. This will try to eliminate most of your confusions regarding which distribution should I choose. Okay. Or a question has been given to me and it is regarding which of the question distributions. Okay. So different type of numerical problems are there. I will try to cover most of these in the future events as well as in the upcoming time which I am having. Okay. Now, when it comes to the engineering importance, discrete probability distributions form the mathematical foundation of reliability engineering. Okay. Because almost every reliability problem involves counting the events. Okay. Means what is the probability of success? How many successes have you achieved? This type of particular problems can only be solved if and only if you are very thorough, you are very clear with the foundation. That is, foundation is nothing but your distribution, probability distribution. So these are typical applications. Okay. Some of the typical applications are there in almost all of the industries. Okay. We generally use this particular concepts. Okay. Reliability engineering, sensor failures, machine breakdowns, manufacturing defects, software crashes, nowadays software hacks also. Okay. And communication packet loss. These losses generally occur in the your transmission, line transmission, or your OFC, optic fiber cable transmissions. Okay. So suppose you are sending 1000 number of data packets, and at the receiving end, you are only able to receive nearly 990 data packets. Okay. So that would be given in the problem itself. Okay. So communication packet losses. These come under our reliability engineering domain. Fatigue failures, failure due to fatigue. Okay, suppose a critical airliner part is there. Okay, and it has run for certain number of hours, say 550 number of hours. So after that, it will be subjugated to fatigue losses. Okay, and your maintenance scheduling, quality inspection, fault diagnosis. Okay, without the probability distributions, engineers cannot estimate the system reliability because we have seen the reliability of the components connected in parallel always increases and connected in series always decreases. This in general is true, okay, that we already have seen. Now we try to see binomial distribution. Okay, first distribution, which you should understand that it's generally of most importance is your binomial distribution. Binomial distribution models the number of successful outcome obtained from a fixed number of independent experiments. Every trial is would be having two possible outcomes, either it would be a success or it would be a failure. Probability of success remains constant through all the trials. Okay. Subject to the condition that there are fixed number of trials, the trials are of independent nature. Okay. Means the outcome of one of the trial which won't be affecting the other. Okay. First trial won't be affecting the outcome of second trial. Okay. Or it is of constant probability means the same. Okay. Probability is not continuous function or a function which is changing. Okay. It does not changes with respect to any of the local variables. Okay. It should have constant probability. There is a binary out. Okay. Binary means either 0 or 1 means two probabilities are there. Okay. That is the thing. Reliability applications include number of functioning sensors, successful packet transmission already told you, working processors, robots in the fleet, operational batteries, likewise. Okay. Trials are not independent, then your binomial distribution cannot be applied. Please, if you are having a notebook and pen, please note it. Okay. Binomial distribution can only be applied if their trials are independent. Okay. This is most important for you to understand. What is the relation? There exists another distribution, which is the Poisson distribution. It is related with binomial only. The Poisson distribution is obtained as the limiting case of binomial distribution n becomes extremely large. Okay, n becomes extremely large. That is one of the condition. P becomes small. Okay, P becomes small. NP is equal to lambda, which remains constant in only those particular cases you will be able to apply Poisson distribution. Okay. Instead of counting successes in a fixed number of trials, Poisson distribution counts random events occurring over continuous intervals, such as your time, distance, area, volume. Reliability examples include hardest failures per month. Okay. These are some of the examples. Okay. Hardest failures per month means a time constant is lower. I told you, right? N becomes very, very large, P becomes very, very small. Okay. And NP is equal to lambda. It remains constant. Okay. These are the three particular conditions in which you have to go with Poisson distribution. Okay. Software crashes per day. Okay. Then vehicle accidents per kilometer. Lightning strikes per year. Customer requests per minute. In all of these cases, you can go with Poisson distribution. Okay. That is the thing. Now you try to see there is a memoryless property. Okay. Memoryless property we already have seen in our previous lecture. Okay. We have tried to prove it also as a limiting condition. Okay. It is satisfied by the geometric distribution. It generally satisfies this memoryless property. Means that previous successful trials have got no information about the future outcomes. The failure or success of the future outcomes is not affected by the previous trials. Okay, that is the case. Means uh, conditional probability of x being greater than s plus t and subject to condition x is greater than s. Okay, this conditional probability, if you will try to see, is will be equal to probability x is greater than t. Means the time constraint factor won't be there. Means previous successful trial will be not affecting the future of the outcomes. Okay. For example, suppose 100 microchips have already passed the inspection, then the future outcome of the next 20 chips, okay, which would be testing, won't be affected by the previous successful operation of the 100 microchips. Okay, this you just try to take an example. Okay, just an example, you just try to understand. Okay, so binomial distribution, okay, this is the comparison chart. Binomial distribution is generally with replacement, hypergeometric without replacement. In case of binomial distribution, we are going to have independent trials. Hypergeometric, we are going to have dependent rights. Okay. Binomial distribution generally has infinite or very large population. Hypergeometric has finite population. Binomial distribution has constant probability. Hypergeometric probability changes after every draw. Okay. In case of binomial, you will be having easier calculations, and in case of your hypergeometric, you will be having more accurate for finite sample. Okay. So binomial approximation may be acceptable if and only if what is the case? Small n over capital N is less than 0.05. Okay. What is small n here? What is capital N here? Okay. This you just try to see from this particular table at the starting only we have just just summarized what are the different types of parameters. Means small n is the number of trials and capital N is your population space. Okay. If small n upon capital N is less than 0.05, okay, you go for binomial approximation. Okay. Otherwise, you need to use the hypergeometric distribution. Okay. Negative binomial distribution generally is used when you are able to answer that how this particular question that how many trials are needed before the case success occurs. Okay. For example, you want to go with third machine failure, fifth defective product, fourth successful communication means the exact instant should be known to you. Okay. This distribution naturally extends the geometric distribution. Okay. Real world engineering examples of the all the distributions are just summarized here. For example, in binomial distribution would be case of working sensors in an IoT network. Poison you can go with equipment failures per month. Okay. Then geometric number of tests before first defective chip. Okay. Then for hypergeometric quality inspection without replacement. Negative binomial means fatigue cycles until the third grade. Okay. These are the examples which do not have probability distributions, support predictive maintenance, reliability estimation, quality control, risk management in modern engineering systems. How the modern engineering systems are built. Formula for your quick referencing are given here. See here, in case of binomial distribution, please note it, this note this table down. Okay, if you are having notebook and pen, please do note it down. It is very, very important and it would be relevant in subsequent weeks also. If you are thorough with this particular knowledge, you won't be facing any problem throughout this course. Okay. So this is very, very important. Please note it down. Binomial distribution, the probability mass function, probability distribution function, same thing is likewise defined like this, NCX. Okay, this is NCX, P raised to power x, Q raised to power n minus x, where P is the probability of success, Q is the probability of failure, means 1 minus P. Okay, then mean is your NP and variance is your NPQ. N is the number of trials, NP is the probability of success, Q is the probability of failure. Okay. Poisson distribution, the PMF is e to the power minus lambda, lambda to the power x over x factorial. Okay. And the mean is what? Lambda. And variance is also lambda. Okay. In case of your geometric probability distribution function, q to the power x minus 1 into p. Okay. Means till qth attempt. Okay. Q is the probability of failure. Okay. So all the events up to a certain number of events they should fail, and after that there should be a success. Okay, that is the prior condition of this hypergeometric distribution, sorry, geometric distribution. Okay. Mean is your 1 by p and variance is your q upon p square. Okay. Then hypergeometric is mcx multiplied by n minus 1 c n minus x, okay, divided by ncn. And similarly, your mean is given here. Okay. Small n, capital N divided by n. And this particular expression is for your variance. Okay. Go for the derivation of this expression. Okay. If you go for the derivation, you will be in a certain position to remember. From this only it has come. Okay. And if you face any difficulty, then please do tell me. I'll explain you that how mean and variance of this hypergeometric PMF has been calculated. Okay. Then in your negative binomial distribution, this is like this: x minus 1, c k minus 1, p raised to power k, q raised to power x minus k. Mean is k upon p, then variance is kq upon p square. Okay. Now you try to see this particular problem. Problem number one: binomial distribution in the component redundancy. Okay. Parallel sensor array in an industrial automation network consists of 8 identified independent sensors. The probability that a single sensor detects system anomaly is equal to 0.85. PN rule: the binomial distribution is appropriate because there are fixed number of trials. Okay, first of all, fixed number of trials and equal to it has been given. Binary outcome is there, either success or a failure. Constant probability of success is there, and independent number of trials are there. Okay, that is the thing. So going for the step-by-step solution. Okay, here n is 8, x is 6, p is 0.85, q is 0.15. Then you go for the probability mass function, the probability distribution function, and substitute the for probability of exactly 6 successful detections. You substitute all the values, all the variables, okay, in the formula. Directly you would be able to obtain 0.2376. That is the thing. After the class is over, please do take this PDF, okay, and try to calculate yourself the values. See how I have plugged the values and got the result. Okay. In case of your system reliability is the probability of obtaining at least one successful detection. Okay, means one successful detection or one successful uh, success should be there. Means using your complement rule. Okay, the system reliability would be what? 1 minus p at x equal to 0 multiplied by p at x equal to 0. Okay. P at x equal to 0 has been given to you. Okay. Directly you would be multiplying, you would be getting this particular expression 1 minus this particular value would be 0.9999. Okay. This is, I think, repeated. Okay. This particular term I have repeated. So please note it down. It will be one time once 1 minus p at x equal to 0. Okay. Probability of obtaining at least one successful deduction that you just have to subtract from 1. Okay. And this particular expression p at x equal to 0 that I have calculated here. P at x equal to 0 I have calculated here. And then I have calculated the system reliability. System reliability is 1 minus p at x equal to 0. Okay, that is 0.9999. Approximately it will come like this. Okay. What is the physical significance? System reliability of 0.9999 is demonstrates that 8-way parallel redundancy effectively mitigates individual sensor failures. Means individual sensor failures are being subdued. Okay, that is the case here. Means the system reliability is increased approximately 99%. High-stake engineering environments, such redundancy ensure that failure of one of the sensors does not result in the catastrophic loss of detection capability. That is the case here. Okay. Now you go for Poisson distribution. Poisson distribution for failure rate modeling. Okay. Means suppose a high traffic cloud server experiences an average failure of rate of lambda is given as 1.5. 1.5 crashes every 24-hour period. Okay, time constant if I'll give and I'll give you the rate of failure, then you go for Poisson distribution. Okay, Poisson distribution models a number of discrete events occurring within a continuous interval. Limiting form of binomial distribution when n is approximately tending towards infinity, p is tending towards 0, and b is given as lambda. Then probability at x equal to x is e to the power minus lambda, raised to the power x and divided by x factorial. Okay. General expression I have given you, lambda is given to me is 1.5 failures per hour. Okay. So try to understand that the time interval which I am putting would be also in hours. So unit should be same. Okay. So exact zero failure would be happening at just I have to put in place of small x, I have to put 0. So e to the power minus lambda, lambda to the power x, lambda to the power x, okay, divided by 0 factorial, that would become 0.2231. More than two failures, you have to calculate probability of x event happening greater than 2. Okay, greater than 2 means 1 minus p at x equal to 0, x equal to 1, x equal to 2 means more than 2 values. That is what we are trying to calculate. Means it should be either 3 failures, 4 failures, 5 failures, plus and so on up to infinity. So that would be coming at as sum of all the events is equal to 1, sum of all the possible events is equal to 1. That is why I have subtracted 1 minus subtracted all the probabilities which are less than 2 from 1. Okay. That is the value, that is the meaning of this particular expression. Okay, calculating the individual probabilities, I have just tried to calculate x equal to 0 already calculated, x equal to 1 I have tried to calculate. Okay, plugging in the expression only, you will be very easily able to obtain this particular expression. Okay, x equal to 1 I have obtained. Similarly, I will be obtaining x equal to 2. Okay, then probability x greater than 2 I will be able to calculate. It would be coming 0.1912. Okay, means there is a 19.2% probability of observing more than two failures within 1 day. Although the expected number of failures is low, the Poisson variance is also 1.5, okay, indicating that sufficient variability to justify standby failover mechanisms, means as per the standards or as per the requirements of the company, you have to be ready with the backup systems. That is what is being conveyed. Okay. Then going for the geometric distribution in time to first failure. Okay. During burn-in testing of microchips, chips are tested sequentially. Okay. First chip, then second chip, then third chip, plus and so on. Okay. So the probability that a certain chip fails is 0.02. It is almost negligible. Testing continues until the first defective chip is identified. Okay. So there is this decision rule that the geometric distribution models the number of trials required to obtain first success. That is first failure plan. Okay, means a defective chip should be identified. It possesses the memoryless property, meaning future probabilities are independent of the previous outcomes. Okay, so writing the probability mass function q to the power x minus 1 into p. Okay, then first failure on the 50th trial, just plugging in the value as 50. Okay. Then expected value is 1 by p. Okay, already I have told you. 1 by p is nothing but 1 by p already has been identified 0.02. 0.02 is given in the problem. 1.02 means 50. Means on an average, 50 chips must be tested before detecting one defective unit. This is very, very important. What the sampling size you will train. Okay. In research as well as in case of your field, in case of your testing, okay, it is very, very important that you should check for the sample size. Okay, this is very, very important. This expectation is an important production planning metric because excessive testing costs may outweigh the economic value of the manufactured batch. Okay, so in the continuing sequence, problem number 4, hypergeometric distribution for quality control sampling. Okay. Suppose a finite production batch contains total boards n equal to capital N equal to 100, defective boards small m equal to 10. Okay. Quality engineering is sampling n equal to 5 boards without the replacement. Okay. So the hypergeometric distribution applies here because the sampling is performed without replacement. Means successive draws are dependent. Okay. That is the case here. Just plugging in the values in the probability mass function. Okay. Probability of exactly one defective bond I have tried to calculate. Okay. Already total number of bolts is given as 100, defective number of bolts is given as 10. Okay, plugging in the values, we would be getting P at x equal to 1 is 0.3394, means 33.94% probability is there, finding exactly one defective bolt in a sample of 5. Since small n upon n is equal to 0.05 in this particular case, the hypergeometric model provides the precision required for audits or for finite populations. Okay, that is the case here. Next is you go for negative binomial distribution. Negative binomial distribution or multi-stage failure. Okay. Yeah, structure fatigue test continue until third fracture occurs. Okay. Use K is given as 3, P is given as 0.25. Then the negative binomial distribution generalizes the geometric distribution by modeling the trial number at which kth success or kth failure occurs. Okay, so that exactly at x equal to 10, if you will try to plug in the values, okay, you would be getting this particular probability expression, and the probability will come as 7.51%. Okay, when 7.51% probability is there, then the footing experiment terminates exactly on the 10th loading cycle. Okay, that is the case here. Okay. Now we go for just a summary table. Okay, I have provided a summary here. Number of successes and trials, if it is required, then you go for binomial distribution. Subject to the condition, independent trials are there with replacement. Okay, that is the case. Number of events in a time or space interval is there. You go for the Poisson distribution. I have already told you the expression also. Large and small p constant event rate is there when you always foresee this particular Poisson distribution. Okay. Trial number of first success is being looked upon. Okay, you go for memoryless binary trials are there. Okay, then you go for geometric distribution. Number of successes in a finite sample is being asked, then you go for hypergeometric distributions. And trial number of k success is the required when you go for negative binary distribution. Okay. Conditions also have been mentioned and appropriate distribution also has been mentioned in this particular table. Okay. So if you try to make a generalized guess, then in which particular case I have to go with which particular distribution and which particular formula I have to apply, then you go for this particular flow chart. Okay, this is a summary flow chart. Okay. So what are you measuring or counting? This has to be decided in the very first attempt. Okay. Whether it is a continuous time or a space interval or it's a discrete trial or uh, uh, unit. Okay. Discrete trials or units are being looked upon. Okay. Means you are counting number of failures over TRs. Then you go for Poisson distribution. If you are testing batch samples, mission cycles, what is the particular sampling method? Whether it is without replacement. If it is without replacement and there is a finite batch size, capital N, then you go for hypergeometric distribution. If it is an independent trial or it is with replacement, then you need to ask what is fixed. Okay. Fixed number of trials are there. Okay. And fixed number of failures are there. If fixed number of trials is there, then counting the success or counting the failure, you go for binomial distribution. Okay. In case of binomial distribution also, you may go for standard binomial distribution. Okay. Or you may go for Poisson distribution. Okay. Depends on you. Particular condition in case of Poisson distribution should be this, that capital N should be greater than equal to 100 P should be less than equal to 0.01 and small n means number of trials is small and you go for standard binomial distribution. Okay. If fixed number of failures is there, then you have to go until the rth failure. Okay. If R is 1, then go for geometric distribution. If R is greater than 1, okay. Number of failures is greater than 1, you go for negative binomial distribution. Okay. That is the in general summary of all the distributions. Okay. Then this is just a summary table. Okay. You yourself can revisit it, and this is the summary I have written here. Okay. Not much is there to explain here, but a particular question, keyword, or the trigger, if it is there, then you have to apply which type of distribution that is what is being mentioned. Okay. So we'll practice some of the problems based on all of these distributions. Okay. Please take a notebook and pen handy. Okay. I'll be putting some of the questions, then you try to solve. And if you have solved it correctly, then please see my solution. Otherwise, if you are not able to solve, then please we'll go through the solution together. Okay. And then after the session is over, please do download this particular PDF. Okay. And then go for solving the question yourself. Okay. This particular link already I have provided in the previous session. I will be pasting it once again. Okay. Link for all the PDFs for everything, every resource would be there. Okay. Let us move forward with this particular question. Okay. Yeah. This is week 2 tier tutorial. Okay. For the course statistical learning for reliability analysis. Okay. And this one is the first typical question. Okay. Yeah. See here, an aerospace engineer must pass a two-stage diagnostic test. Probability that an engine passes stage 1 is 0.90. The probability that stage passes both stage 1 and stage 2 is 0.82. Evaluate the system if an engine has successfully passed stage 1. What is the probability that it will pass stage 2? Okay. Try to calculate. Do try to calculate this particular question. Okay. What is being asked? What shall be the approach? What should be our answer? Already with great detail I have tried to explain. Okay. If you have noted down each and everything, very easily you would be able to solve it. Okay. To solve it. 0.81. Okay, good, very good. Let us check. Okay, let us check that what is the correct option. It's 0.90, not 0.81. Okay, we'll just go through why is it so. Let S1 is event is passing at stage 1. Let S2 is there such that event is passing stage 2. Then given S1 is 0.9190. Okay, you have to find out that S1, if the engine has successfully passed stage 1, what is the probability it will pass stage 2? Means S1 intersection S2 you have to just calculate. Okay. That has been given as 0.81. Okay. The probability that it passes both means intersection. Okay. And means union. Okay. Means what has been given that it passes stage S1 means P S1 has been defined as 0.90. Then S1 intersection S2. S1 intersection S2 has been given as 0.81. Okay. Means intersection, what is the meaning? Means it passes both stage 1 and stage 2. Okay. Means and would be the means both the events has to simultaneously take place. Means intersection would be there. Okay. And is there, okay? Stage 1 and stage 2. Yes, simultaneously. That is why you go for intersection. If or is there, okay? If it is given or, then you will do union then, okay? Then you will write union. Okay, please do understand. If intersection is used when keyword and is there, okay? And if or is there, then you go for union. Okay, that is the thing. Please do remember. If an engine has successfully passed stage 1, what is the probability it will pass stage 2? Okay, means S1 has been given as 0.90, then S1 intersection S2 has been given as 0.81. Now you are being asked the conditional probability. Okay, S2 given S1 has already passed the test. Okay, means conditional probability is being asked. Okay, S2 over S1. That is nothing but probability of S1 intersection S2 divided by S1. Probability of S1. Okay. 0.81 divided by 0.90. It would be nothing but 0.90. When in calculation mistake is there, then it would be something else. Let me just divide it. Check. Okay. 0.81 divided by 0.90 would be coming exactly as 0.1. Okay. So there is no confusion regarding this particular problem. Okay. Answer would be 0.91. Okay. You can see. Okay. I have also calculated with you. Okay. So conditional probability that S2 passes the test given that S1 has already passed the test would be 0.90. Conditional probability restricts your entire universe to the engines that survived stage 1. If you are measuring this surviving 81% relative to the 90% pool, not the original 100% pool. It will be straight to remaining. Okay. So I hope this particular problem is clear. Okay. It was an easy problem. Okay. Let's go forward. Move to the second problem. Keep on solving, okay? Don't feel that you are not achieving the correct option in the very first attempt. No problem. Let's have just a practice session. But the approach as well as the rationale which is behind solving this particular problem should be clear to you. Okay, that is mine. A plant manufactures microchips across two lines. Line A produces 60% of the volume with a 2% defect rate. Line B produces 40% of the volume with a 5% defect rate. During final inspection, a chip is found defective. What is the probability it was manufactured on line B? Okay. You try to formulate in the same manner in which I formulated the previous problem. Okay. Bayes rule in the quality control means Bayes theorem would be applied in solving this particular problem. Take good amount of time. Okay. First of all, formulate the problem, then do try to solve it. Okay. See here. Okay. Shall move forward. See here, probability, the correct option would be 62.5%. Okay. Why is it so? We'll just see. Plant is manufacturing microchips, okay, across two lines. Line A produces 60% of the volume with 2% defect rate. Line B is producing 40% of the volume with 5% defective rate. Okay. 60% is produced by line A, 40% is produced by line B. Okay. And how many number are good and how many number are defective? Okay. So defective percentage has been given. Okay. 60% with 2% defect rate. Okay, 60% defective rate is 2%. Okay, 2% means 0.02. Here it is written 0.012. It won't be 0.012, it won't be 0.02. 60% with 2% defective rate, line B produces 40% with 5% defective rate. 40% with 5% means 0.05. Okay, that will be the value. Okay, okay, here it has been mentioned as the probability. Just one second. Hello, sir. तो क्या ही कर सकते हैं मतलब अब ऐ- हाँ ऐसे ही कर देते हैं मैं प्रॉब्लम बात की बात में लिख दी जो चलिए बस चलिए so probability of the defect D would be if it is produced by line A, okay, and it is a defective product, that this particular condition has to be applied simultaneously, means and would be there, and means multiplication, okay, or it is produced by line B and it is defective. Okay. So produced by line A, okay, that is 60%. What is the probability it is defective? 2%, 0.02. Then probability it is produced by line B, that is zero point 0.4, and it is defective, that is 5%. And these two are in OR condition, means sum would be there. Okay, plus sign would be there. So if you will try to add these two different probabilities, you will be getting 0.032. Okay. If you go with the Bayes theorem, means it's a defective product. Okay. It's a defective product. And what was being asked in the question, that what is the probability it is manufactured on land? Okay. It has been given that it's a defective product, and what is the probability that it is manufactured by line B. Probability that it is manufactured by line B, given that it is defective. Okay, it is defective. Try to apply the Bayes theorem. It would be giving probability B over D is given as B intersection D divided by probability D. Okay, probability of happening of this D event or defective product is already we have calculated as 0.032. Okay, and then you try to calculate B intersection D, B intersection uh, D. Okay, already we have just calculated. Okay. That would be 0.020, this particular part. Okay, this particular part of this expression above. Okay, B intersection D over probability D. Okay, 0.020 divided by 0.032. 0, this B intersection D already we have calculated. Probability that it's defective product and it's produced from line B. Okay, so 0.05 multiplied by 0.40. 0.40 multiplied by 0.02. Okay, that should be the case here. So it is 0.020 divided by 0.032, that is 62.5%. Okay, that's the case here. Okay, so in this format manner, you have to solve the questions regarding the probability distribution. Okay. Next problem is this one. A component's discrete lifetime x in months has been the following probability mass function. P1 has been provided to you as zero point 0.1, P2 has been provided to you as zero point 0.2, P3 is zero point 0.3, P4 is zero point 0.4. Okay, what is the reliability of component at 2 months? Denoted as R2, means probability it is survived beyond 2 months. This particular thing you have to calculate. Okay, do try to calculate it. Do try to calculate it and tell your opinion in the chat box. Okay.
Sir, bias theorem, how we can remember such a formula?
No formula is required here. Probability mass function directly value we have provided to you. P1 has been provided, P2 has been provided, P3 has been provided, P4 has been provided. For this particular problem, no remembering of formula is required. Okay. And the
Previous,
ta and the table which I have mentioned, you have to remember that. There is no other way around it. Okay. One table I have provided in this particular explanation at the end, starting or at the end, I have I don't know. This particular table. This you have to remember. It will come with practice. Okay. This you have to remember, but for this particular problem, no formula is required. Okay. Directly you can calculate E at x greater than 2. Probability of reliability of the component at 2 months or probability it survives beyond 2 months. That can be directly calculated because PMF values we have given to this particular problem. Okay. Don't worry, I'll solve. Then you will be having a better idea how to solve this type of problems. See in this particular problem, you just see correct option would be 0.7. Okay. How is it coming? Cumulative distributive function. Okay. For the CDF, if you will try to calculate, okay, probability of failure by a month, 2. Okay. What has been given in the question? Reliability of the component at 2 months, that is being asked. Okay. R2 is being asked. Probability it survives beyond 2 months. Okay. That has to be first taken into account. Okay. Here I have written greater than 2. Okay. It won't be greater than 2. It will be less than 2. Why is it so? Reliability at 2 months. Reliability is being asked. Okay. I didn't read it. The reliability is currently being asked. Okay. And reliability is nothing but 1 minus probability of happening of an event. Okay. So the reliability at 2, okay, means the reliability of component at 2 months. Okay. It would be 1 minus p at x greater than 2. Okay. Greater than or equal to 2. Okay. Or p less x less than equal to 2. Okay. Same thing as equal to 2. So it would be p1 plus p2. Zero point 0.1 plus zero point 0.2. Okay. Reliability formula if you will apply, then R2 would be 1 minus the p of x. Okay. 1 minus p of x. This is small fx is nothing but p of x. Directly we have calculated it has zero point 0.3. So 1 minus zero point 0.3 would be equal to 0.7. Okay. This P of x or f of x tracks the accumulation of dead components. Means if the reliability function would be like this, a step up function, okay, like this, if it is there, then the probability function would be 1 minus this particular value. Okay, 1 minus this particular value f of x or cumulative distributive function. Okay, 1 minus of this particular value. Okay. So f of x tracks the accumulation of dead components. Rx tracks the surviving population. They are perfect inverses. Okay, inverse of one another. R2 represents 70% of the components still functioning at the start of month 3. Go to the case here. See here, next problem. An electromechanical actuator has a discrete lifetime distribution. Test data reveals that the expected value of x is 10 million cycles. Expected square of the lifetime, that is ex square, that would be 104. Calculate the standard deviation of the actuator's lifetime. Okay. Standard deviation value we have to calculate. Do try to recall the expression, and if you are able to calculate, it is fine. Otherwise, I have calculate. See, for solving these all of the problems, one of the prerequisite is you have to go through the entire week's content. Okay, that we have pre-released. Just have to go through it. Okay. Afterwards, you would be giving some of the assignments. You have to solve those. This is a general session, general discussion session. If any doubt is there, feel free to ask. Otherwise, if any particular problem you are facing, feel free to ask. Or just for recalling the concept of the entire session. Okay. That is the primary purpose of holding this particular session. Okay. But prerequisite is that you have to be thorough with the entire week's content that is pre-released. Okay. Then only you would be able to solve these particular problems and you will be able to revise. And your grip on the subject will be increasing week by week. Okay. And at the end of the 12 weeks, you would be having no problem with the entire content. I hope so. Okay. Just have to revise the entire thing and sit for the examination. Okay. This is the flow which I am expecting from you. Okay. Be thorough with the content week wise. Okay. That is what my request to you guys is. Okay. See here, directly the expression must have been explained in the theory classes. Okay. Variance is nothing but expected value x square minus expected value of x whole square. Okay. So expected value of x square, okay, that has been given as 104 in the problem. Expected value of x has been given as 10. So 104 minus 10 whole square, okay. 104 minus 100, that would be giving you 4, okay. So your standard deviation would be nothing but under root of variance of x. Variance of x we have calculated as 4. So standard deviation would be a root of variance, that would be equal to 2. Okay. Variance is in squared cycles, a mathematically useful but physically meaningless unit. Okay. Square root of the standard deviation restoring the measurement to physical cycles to quantify predictability. Okay. So mean distribution or the probability distribution is like this, then this particular line would be your mean. Okay. The probability distribution, if it is like this, then this will be your mean. This is mean plus minus one time of standard deviation. That would be covering this many number of values. Okay. That is the case here. Okay, very simple expression is there. Okay, already must have been covered on the theory part. Okay, so the correct option would be your B, that is 2. Okay. Variance of x directly you will calculate, then you will try to say that the standard deviation would be under root of variance of x. Okay. Under root of 4, that is good. Two. That is the case here. Now, moving forward to the next problem, a critical flight control module utilizes 4 redundant sensors. The probability of any single sensor failing during a flight is equal to 0.1. System requires at least 3 sensors to be working uh, to be working to function correctly. What is the total probability of total system failure? Probability of total system failure that you have to just calculate. Okay, who try to calculate it? Already I have told you how to pick up the particular distribution. Okay, if you have got it exactly, then very easily you would be in a position to solve this particular problem. Okay. See here, okay, you have to just calculate the system requires at least three sensors to be functioning correctly. What is the probability of total system failure? Okay, P is given as 0.1. Okay, probability of any single sensor failing. Okay, correct answer would be 0.0523. Okay, 0.0523. That is A would be correct. Okay, why is it so? X is number of failures. The system fails if P at X is greater than equal to 2. Means P at X greater than equal to 2 would be equal to 1 minus P0 plus P1. Okay. P0 and P1 you would be adding. Okay. So four redundant sensors were there. Any sensor failing is 0.1. At least three sensors need to be failed. Okay. At least three. Means at least three means greater than equal to 2. Okay. That would be a particular case of binomial distribution. Okay. So 4 out of 3. Okay. 4 out of 3. Okay. Four redundant sensors are there. At least three sensors need to be functioning correctly. Okay. This is a typical case of binomial distribution. Okay. When a whole bunch has been given, and out of those many number of sensors, this many number of sensors are required to function correctly, or this many number of sensors have to be just uh, out of function. Okay, then this comes under typical case of binomial distribution. Okay. So probability of this system fails if x is greater than equal to 2 means 1 minus p at x equal to 0 plus p at x equal to 1 you have to calculate. P0 is 4c0, then p to the power NCR, p to the power r, okay, q raised to power n minus r. This is the general expression. So using that 4c0, 0.1 to the power 0, zero point 0.9 to the power 4, you will calculate 0.6561 would be coming. Then P1, if you will try to calculate, it would be 0.2916, and directly you will be plugging in this particular expression. Okay. Means, first of all, at least three sensors need to be working. Means more than two have to fail. More than or equal to two. That would be a total system failure. Okay. At least three need to be functional. Means more than two have to fail. Okay, two or more than two have to fail. So directly we have formulated and we have tried to calculate this particular expression. Okay. Binomial combinations account for all physical permutations of failure. Instead of calculating the many ways, two, three, or four can fail, subtract the highly probable safe states, that is 0 or 1, failure case from 100%. Okay. That is it. Moving forward to the next problem. Directly I have mentioned Poisson distribution. I shouldn't have mentioned. You ultimately have to guess yourself in the examination. But you would be very easily able to guess if you have listened to me previously. A data center experiences rare power surges at an average rate of lambda equal to 0.02 surges per hour. The servers operate continuously for a t equal to 100-hour interval. What is the probability of experiencing at least three power surges during the interval? At least three power surges. Okay. Try to calculate. Yes, you try to see here in this particular problem, what is the probability of experiencing at least three power surges during the interval? That is what is being asked. Okay. So the mu, okay, or the center experiences rare power surges at an average rate. Rate has been already given to you as 0.02 surges per hour. Okay. It operates for continuously t equal to 100-hour interval. What is the probability of experiencing exactly three power surges? Okay. So exactly three power surges can be directly calculated using the Poisson distribution. Okay. Because the rate has been provided to you and per time interval it has been mentioned in the question. Okay. So 0.02 surges per hour multiplied by 100 hours means lambda into t we are trying to calculate, that is 2 surges. Okay. And directly at x equal to 3 I'll try to formulate the particular probability p at x equal to 3 because I know the expression, it is e to the power minus lambda raised to power t. Okay. E to the power minus lambda raised to the power t over the factorial of that particular expression, e to the power minus mu to the power k over k factorial, e to the power minus lambda raised to power t over t factorial. That is the general expression. Okay. So e to the power minus 2, 2 raised to power 3 divided by 3 factorial. If you will try to calculate, it is 0.1804. Okay. So unlike binomial, which has discrete slots like these answers, Poisson models event occurring randomly along a continuous continuum. Okay, the lambda must be scaled by a exposure timeout t to find the t parameter. Okay, that is in general the case. Okay, so probability of experiencing exactly three power surges we were asked to calculate. Okay, that we have calculated t at x equal to 3. Okay. Next problem, an automated testing rig sequentially cycles power to a high voltage switch. The probability of switch failing on any given cycle is P equal to 0.05. What is the probability that the switch operates perfectly for the first three cycles and fails on exactly the fourth cycle? Okay. What is the probability that the switch operates perfectly on the for the first three cycles and fails on exactly the fourth cycle? Okay. This you will just try to calculate. Okay. See here, the correct option. Okay. It's a geometric distribution and first failure question. Okay. An automated test rig sequentially cycles power to a high voltage switch. The probability of switch failing on any given cycle is equal to 0.05. What is the probability that switch operates perfectly for the first three cycles? Okay. For the first three cycles, it has to fail. It has to perfectly operate. Okay. And fail on exactly the fourth cycle. That is the key word for you to decide. It will go for geometric distribution. Okay. So X is the trial number on the first failure. Okay. Probability at X equal to 4. Okay. That is 1 minus P or Q. Q raised to the power K minus 1 multiplied by P. Means Q is 1 minus 0.05 because probability of switch failing has been directly given as 0.05. Okay. So 1 minus 0.05 raised to the power k minus 1, 4 minus 1, that is 3 multiplied by 0.05. Okay. So if you will try to calculate, you will get 0.042. Okay. means success, success, success. In all three in sequence means three for the three times it has to exactly undergo success. Okay. And after that, it should be a failure. That is this particular one. Okay. So 0.95, 0.95, 0.95 multiplied by zero point 0.0. Okay. It is 0.95 raised to power 3 multiplied by 0.05. Okay, that is 0.042. It means geometric distribution relies on memory-less property. So it does not accumulate fatigue in this particular model. The probability of failure on the fourth cycle is simply the probability of surviving three times multiplied by a fresh independent 5% chance of failure. Okay. So this is the expression. Next is a sealed batch contains 10 industrial valves, three of which have defective seals. An inspector randomly selects a sample of four valves for testing without replacement. What is the probability of finding exactly two defective valves in this particular sample? Okay. This is a hypergeometric distribution of batch sampling. Okay. This particular problem is regarding hypergeometric sampling. Okay. You try to see here in this particular question, okay, the correct option would be this one, okay, 0.300, okay, means it's a hypergeometric probability mass function. How we have just reached to this particular conclusion, okay. See here, several keywords are there in the question itself. A sealed batch contains 10 industrial valves, three of which have defective seals. Inspector randomly selects a sample of four valves for testing without replacement. Without replacement is there. Okay. Randomly selection of sample of four valves for testing is there. Okay. What is the probability of finding exactly two defective valves in the sample? Means exactly two defective valves that you have to the probability you have to just calculate. Okay, so definitely it would be a hypergeometric distribution question. Okay, so the expression I have already told you, it would be like this. Okay, we at x equal to 2, we will try to calculate. Okay, probability of finding exactly two defective. Exactly two is there, not greater than equal to two, not less than equal to two. Okay, So x equal to 2, you will try to calculate 3c2 and multiplied by 7c2 divided by 10c4. Okay. So if you will try to calculate the exact expression, would be coming as 4, 3 only. No particular doubt is there. Exactly it would be coming. If you are having any problem, feel free to see the solution. Okay. Unlike the binomial model, sampling without replacement changes the odds with every drop. Removing a defective valve fundamentally alters the ratio of good to bad in the remaining batch. Combinatorics perfectly accounts for this shifting reality. Okay. Then another question of mixed type means Poisson approximation to the binomial. Okay, mixed Poisson and binomial distribution question is there. Massive server farm is there containing n equal to 5,000 individual nodes. Okay, directly if small n means the number of observations is too large a number, you will go for Poisson distribution. Okay. The probability of any single node failing on a given day is incredibly small. That is 0.001. Using Poisson approximation, what is the probability of experiencing exactly four nodes? Exactly four nodes of failure. Okay. Just plugging in the values in the expression will give you the answer. Don't try to calculate. So directly, if you do plugging in the values, okay, you would be getting C. Under the conditions that they have to be met for this particular approximation, that is lambda, which is np. N into p means n is very large and p is very very small. So lambda, that is n into p, that we have tried to calculate, that is coming as 5. Okay, and exactly plugging in the values e to the power minus lambda, lambda raised to power t divided by t factorial, it gives us the probability at x equal to t. Okay, so e to the power minus 5, that expression is there. Then 5 raised to power 4 divided by 4 factorial, that is 0.1785. Directly, this particular question is very easy to handle. When modeling massive systems with rare individual failure probabilities, computing 5,000 factorial is typically unnecessary. Poisson approximation acts as a mathematical bridge, converting discrete massive scale probability into simple exponential function. Okay, that is the thing. This particular expression, if you will calculating it, will take a lot of time. Okay, this is a very complex calculation, so that is why we have devised a particular method in order to shorten the calculation and approximate the results using binomial expression. And in which particular cases we have to apply where n is very very large and probability of success is very very small. Okay, there we have to apply this particular distribution. Okay. Last particular problem, an industrial fluid pump fails according to a Poisson disk process with an average rate of lambda equal to 1 failure per year. Factory incurs a fixed annual maintenance based cost of $2,000 plus a replacement cost of $5,000 for every failure that occurs. What is the expected total annual cost for this firm that you try to calculate? Okay. See here, X will follow a Poisson distribution with lambda is 1. Why is it so? Because same particular situation is there. Okay. Lambda already has been given one failure rate per year. That is very, very small value. Okay. So for you just have to calculate the expected total cost. Okay. Expected total annual cost. Okay. So total annual cost, first of all, for replacing one unit is base cost of 200 plus a replacement cost. That is $700. Okay. Total 200 plus $700. Okay. So expected value in case of a Poisson distribution, it is nothing but linear, linear distribution. Okay. So directly we have made a cost equation means however units we would be replacing, replacement cost is 500 per failure. Okay. So it is dependent. Okay, 500 per failure, it is a dependent function and base cost is 200. So from there, we have formulated a particular expression that is 200 plus 500 into x. Okay, it is expected to follow a linear uh, cost. Okay, linear cost function is expected to follow a linear uh, distribution. Okay, linear particular function is expected. Okay, expectation x is linear operator. You can seamlessly map the statistical physics of a component directly to the financial ledger of the corporation. That is what we have done in this particular expression 200 plus 500 into x. Okay. So directly plugging in the value of x as 1. Okay. Number of failures per year if lambda is put as 1. Okay. So that would be coming as 700 for us. Okay. So 700 would be the total cost. Okay. Just we have formulated a simple expression for the cost that is base cost 200 plus 500 times of x. Okay, 500 times of x where x is the failure rate. Okay, per failure. Okay, so here it has been given as one failure per year means x is replaced by one. So 200 plus 500 will be coming as 700. So very simple expression is there. Okay. Even this type of questions may be asked in the examination. So I've tried to cover all of the type of questions which can be asked in the examination. Expected cost of evaluation. Okay. So this marks the end of the session. Okay. Week second. Okay. Do revise these handouts I'll provide to you. Okay. And if any doubt is there, feel free to ask. Rest you can kindly leave. Then thank you all for joining the session. Do join the session next week, same time, same week. Okay. Yeah, you will be getting the questions, the recording of this particular session, each and everything on this particular Google Sheet link, which I've shared with you. Okay. If it is not visible to you, I'll share it once again. Okay. You'll open it, then you would be able to see the recording as well as the a particular Google Drive link is there. On that, I will be uploading all these questions, the notes, the handouts, each and everything. Okay. Okay. Where to find more questions like this? See, it is not regarding how many number of questions you are practicing. First of all, go through the questions which ma'am is covering. Okay. In the video lectures, whichever are the problems which she is covering, be thorough with them. Okay. Then you go to the assignments, which you have to necessarily submit for evaluation. Okay. Then third part is this particular session which I am holding. If these three in these three particular areas, if you will be covering enough number of problems, you won't be facing any problem in the examination. Okay. So no need to look hither and thither regarding the questions. Just the problems which I am sharing and which the problems ma'am is sharing as well as the assignment problems. Do revise them continuously. Okay. And the logic should be clear in the examination that what is the nature of the problem which I am being asked in the examination or the question, okay, and which particular distribution function I'll have to apply. The logic should be clear to you, and you should be able to achieve the outcome on your own. Okay, here I am solving for you guys, but in the examination I won't be there. So the logic should be clear to you. Okay, for each and every week, see 10 number of problems will be from the assignment. Nearly 10 number of problems ma'am would be covering in the video lectures and 10 number of problems I'll be covering. 30 number of problems are more than sufficient for you for practice. Okay, in 12 weeks you would be having 360 number of problems. Okay, so this is more than sufficient for you for from the examination point of view. Okay, and if you are very interested, then any statistical book you can just pick it up and try to solve the examination, try to solve the problems which are there at the end of the chapter. Okay. Any statistical book, okay, which is available online or offline will be more than sufficient. Okay. That is the case here. But firstly, your priority should be the content which we are delivering. Okay. If you are thorough with that, then feel free to go through any of the book. Okay. That is the thing. Okay. I hope that I am clear. Okay. Thank you once again for joining the session. Okay, do join the session next week, same time, same link. Okay, thank you all. I'm leaving the meeting for you. I'm ending the meeting as well as for you all. Okay, thanks. Have a great day.